Hello, my name is Miguel Fuentes. I'm here with my teammates Sarika, Aggarwal, Shreya, Gupta, and Aviva, Prins. Our project is risk assessment and measurement of privacy leaks within Google's Ads Data Hub, and we are the Google team. Sarika is going to start us off with an introduction.
Thank you, Miguel. Okay, so this is just an overview of what we will be talking about today. First, we'll go through some background information to introduce our goals for the summer. Then we'll discuss the current and existing special unique detection algorithm, SUDA for short, how we're modifying it to create our new risk measure, the probabilistic identification risk and attacker threat estimate, some results we've gained from using R-score on Ads Data Hub data, and then some concluding remarks, which includes a summary and recommendations for future work. So just some background about our sponsor, Google. Their mission is to organize the world's information and make it universally accessible and useful. It's become present in the day-to-day lives of billions of people, as many of you probably know, through popular platforms and products such as Google Maps, Gmail, and Google Chrome. Their corporate headquarters is located in Mountain View, California, but they also have another office here in Los Angeles that focuses on advertising sales teams and engineering operations. Specifically, this means their platform Cardboard, Chrome, YouTube, quantum computing, storage infrastructure, and most importantly for our project, ads. So Google currently works with advertising companies to create ad campaigns and place ads appropriately. They've also developed this system, Ads Data Hub, or ADH for short, to improve advertising efficiency while maintaining end user privacy. For our project, it's important to understand how Ads Data Hub works. So first, Ads Data Hub imports Google's own event-level data, as you can see here in the blue, into this system called BigQuery. The customer, which is Google's customer, also known as an advertising company, then can import their own data about this same ad campaign. The customer then writes a query. A query is just a request for information that joins both of these two data sets together and then generates some reports and analytics about that specific campaign. It's important to note that customers do not have access to any raw data, only through the specific queries that they choose to write. So in Ads Data Hub, there is an aggregation constraint called k-anonymity that is employed. This aggregation constraint is employed because the idea is if that customers only receive aggregate results, that end user privacy is maintained. So k-anonymity is defined as it filters the query results so that only rows that contain the aggregate information of at least k users are returned. I know that's a little confusing, so we're going to walk through an example. So let's suppose k equals 2 in our case. We have this input table with ID number, age, and gender, and we have a customer that writes this query right here. All this query asks for is the count grouped by age and gender. So here in the top 4 rows, we can see that we have 4 rows that have the age equal to 20 to 29 and gender equal to male. Since 4 is larger than 2, this would be appended to our output here, and we would see age is equal to 2029, gender is equal to male, and count is equal to 4. However, you can see in some of the rows, there's only one individual that has that specific age category and that gender. So here in row 5, we see 20 to 29 and female, and here in row 7, we see 30 to 39 and female. Since 1 is less than 2, nothing is appended to our output. Okay. So even with an aggregation constraint, privacy leaks can still occur. A privacy leak is any divulsion of a user's information. There are 2 types, targeted and volume, which is also known as an untargeted leak. A targeted leak reveals private information about a single end user of interest, whereas a volume attack reveals private information about multiple untargeted and unidentified users. Both of these types of leaks can happen maliciously or unintentionally. So obviously, privacy leaks are not just limited to Ads Data Hub. So a prominent example that we'd like to introduce is the Netflix Prize dataset, whereas previously thought that removing names and addresses would be enough to anonymize this dataset. However, researchers were able to use seemingly benign information, such as movie ratings or when a person watched a movie, to reveal a user's full watch history. This in turn revealed sensitive information, such as religious or political affiliation. Other companies that have had privacy leaks include eBay, Facebook, Delta Airlines, and Uber. So our goals for this summer were to identify and classify leaks. We essentially wanted to develop some sort of methodology to measure the risk of privacy leaks occurring in Ads Data Hub, if any. So a more specific task with this, since that's kind of still really broad, was we set out to find which attribute sets could identify a particular row. All an attribute is just a variable in our data set. So the naive approach would be to exhaustively search for every single combination of attributes and see if that could identify a row, but this is computationally inefficient because the time complexity becomes n factorial. So this is where SUDA, the Special Unique Detection Algorithm, comes in. This is an existing algorithm in a field called Statistical Disclosure Control, and its focus is on finding individuals in a data set that have unique characteristics. The idea is if an individual has unique characteristics, then they have a higher probability of being re-identified, and therefore they could uniquely identify the row. So I'm just going to introduce one term, a minimal sample unique, also known as an MSU, that's going to continue to come up throughout the rest of our presentation. So a minimal sample unique is defined here as that some rows in a data set will have at least one set of attributes that can uniquely identify the record. If no subset of this set of attributes that I'm defining as U, sorry, I know this bad, uniquely identifies the record, then U is going to be denoted as a minimal sample unique. Again, I know this is confusing, so we're going to walk through an example. So let's pretend we have this larger data set here. It has age, gender, country, language, and campaign ID. So as we can see in row 4, this row is the only row that has country equal to United States and language equal to English. There are no other rows in this data set that have that specific combination of attribute values. You can also see that age and country is an MSU for row 4. No other rows in this data set have age equal to 20 to 29 and country equal to United States. As a result, those two attributes, country and language, age and country, are MSUs. So we can see here that gender, country, and language is not an MSU for row 4 because country and language is a subset of those attributes that can uniquely identify the record. We only care about minimal sample uniques because that's all an attacker would need to know. So now I'm going to pass it on to Shreya to discuss how we find these minimal sample uniques using the SUDA algorithm.
Thank you, Sarika. So I'm going to talk about how SUDA does what it does using an illustrative example. So SUDA is a recursive algorithm that computes the MSU candidates that Sarika talked about at every step in a depth-first manner. To elaborate on a little bit on that, this is a rough, very top layer overview of how SUDA functions. It can be a bit overwhelming to go all of it at once, so we'll be going over them in a sequential manner. This is a reference data set that we would be using to illustrate how SUDA functions. To get a bit familiarity with it, it has 5 columns, as you can see: age, gender, country, language, and the campaign ID of the advertisement that a particular person saw. These are the column names that we refer to when we call as attributes, and all the values that these attributes can take are what we call as an item. An item can be country is equal to India, language is equal to Hindi, or campaign ID is equal to 1. The first step in our SUDA algorithm is to generate the item list. So an item list is the collection of all the items that exist in our data set along with the frequencies with which they appear. For example, in this reference data set that we have, this is the item list. As you might notice that campaign ID is equal to 1 is present in all the rows in our data set. That means that if an attacker came to know the campaign ID of a particular person's watch history, there is no essential information that the attacker came to know, and he would not have any potential to identify any particular row uniquely. This is why we cross campaign ID is equal to 1 from our item list. This essentially means that we cross out every item in our item list that appears in all the rows, since these items do not have the potential to identify any row uniquely. This is the first count check that we deploy. The second count check that we deploy is the count is equal to 1 check. This means that we cross out all the items that appear uniquely in our data set and append them to our candidate list for that particular level. The candidate list is what we use to keep a track of all the MSUs that we have found so far. After doing that, we iterate over all the items that are left over in our item list in a sequential manner. The first item is age between 30 to 39. This is what we will call as a reference item. So so for this reference item, we generate the subdata, which is comprised of all the rows in which this particular item was present. As you can see, there are 3 rows in our data set that have age between 30 to 39 of the person that was present in this row. After generating the subdata, we recursively call our SUDA algorithm, this time on the subdata that we got. As done before, we generate the item list for these 3 rows, and we cross out all the items that appear in all the rows, add all the items that appear uniquely in a fresh candidate list too. Doing that, we again pass over to all the items that remain in our item list in a sequential manner. The first item is gender is equal to male, and it has 2 rows in the subdata that we got previously. As done before, we generate the item list. For reference item, gender is equal to male. This time, we cross out all the items that appeared in all the rows, added all the items that appear uniquely in a fresh candidate list 3. If you notice here, after doing that, we have iterated over all the items in our item list. This is the point where we hit our stopping condition, and we return the candidate list 3 that we had gotten so far. Now we want to combine, now we want to check if it is safe to combine all the items in candidate list 3 to candidate list 2. So this becomes the potential candidate list, the candidate 3 that we got, because it has the potential to identify some specific rows that we got so far. But before combining, we want to ensure that these items in candidate list 3 have they meet all the criteria of what we called as an MSU when Sarika defined it previously. This is where merge checks come into picture. We deployed 2 kinds of merge checks to ensure that these follow the properties of an MSU. These are the ranking constraint and the special row check. The ranking constraint helps us to ensure that there is no redundancy depending on which order we saw the attributes from. And the special row check, it helps us to ensure that the MSU that we have is in fact a minimal sample unique. It is also important to note that we check for the special row check when we have more than 1 items in our MSU candidate list. That means for our candidate list 3, if you can see, it contains of singular items, so we will not be deploying the special row check in this case. We'll be deploying that later on. So for the ranking constraint, the implementation wise, we check if every item in our MSU candidate is ranked below our reference item. So this essentially means that since for this level we have gender is equal to male as our reference item with which we generated the subdata, we check if every item like country is equal to India is ranked below our reference item. Since this is not the case, this means that we have already seen this attribute value pair before and we remove it from our candidate list 3. The same happens for language is equal to English, which is also ranked above our reference item. For country is equal to United States, since it is ranked below our reference item, we keep it intact in the candidate list 3, and the same happens for language is equal to Hindi, which is also ranked below our reference item. Now once we have done that, we have checked for all the attributes that were there in our candidate list 3, and we add our reference item which was gender is equal to male with our candidate list, and we append it to candidate list 2 that we previously had. When we have done that, we are done investigating gender is equal to male, and we move on to the next item which is country is equal to United States. As you can see, country is equal to United States is present in the bottom 2 rows, for which gender is equal to female and male is able to uniquely identify row 7 and row 8 in its own self. But since both of these items are present above country is equal to United States, they will fail our ranking check, and hence our candidate list 2 remains as it was before it. For language is equal to Hindi, since it's the last item, that means that we will not generate any subdata for it, because if there existed any other attribute which when combined with language is equal to Hindi is also able to uniquely identify any particular row, that means we would already have covered it previously, and hence it would again fail our ranking checks. At this point, we are done iterating over all the items that exist in our item set, and as you can guess, we have hit our stopping condition, and we return our candidate list 2 as a potential MSU candidate list to be combined with our candidate list 1 that we had in the very first step. So this is the candidate list 2, and we want to see which items in our candidate list 2, when combined with our reference item, this time age, are able to uniquely identify rows, as well as they follow the properties of an MSU. So we'll be deploying merge checks to do the same. The first merge check was a ranking constraint. In the ranking constraint, you can see all the items are present below our reference item, and hence they all pass the ranking constraint. The problem comes in for row 8. As you can see, you need a combination of attributes to identify the person who is in row 8. This is what our ranking constraint cannot cover up, and this is where we introduce the special row check, since there exists a possibility that a subset of those attributes can also identify a particular person. So a special row essentially is any row that has the same attribute values that our candidate list had, but a different value for our reference item. Since row 4, as you can see, it has the same value of gender and country as our row 8 does, but it has a different value for age, which was our reference item. That means knowing the age of the person in row 8 was imperative if you wanted to identify row 8 uniquely. If in case this row 4 was not present, that means knowing just the gender and the country of the person in which who belonged to row 8 was enough to identify that person uniquely, and knowing the age of the person in row 8 added no extra information, and hence it was not required. Once we have passed all the candidates in our candidate list 2 through both of our ranking checks and the special row check, we append them with our reference item to our candidate list 1. At this step, we are done investigating age as our reference item, and we move on to the next item in our item list. We do so for all the items in our item list until we hit the final stopping condition, wherein we have the final list of candidate MSUs, which we return to form a table that looks something like this. Now, I would like to call my teammate Aviva to tell us how these MSU candidates translate into a risk assessment model that Sarika talked about.
Thank you, Shreya. So the first way that we'll use minimal sample uniques in order to calculate re-identification risk in our data set is on the columns in our database or attributes. And this is called a column contribution. It measures how much each attribute contributes to the overall re-identification risk of the data set. It's calculated as follows. For every MSU where an attribute is present, we take 1 over the size of that MSU, summed over all such MSUs, as I said, and then normalized by the number of MSUs in our data set. So if we look at an example, we see here that we have some subset of our previous data set where we've already computed the minimal sample uniques that are shown here. We're going to calculate the column contribution of the age category. And we see here that where age is present, we take 1 over the size of the MSU where it is present. We repeat this for all of the MSUs, sum them, and then divide by the number of MSUs, which in this example is 7, to get a total contribution of 20%. The nice thing about this score is that the more times that an attribute is present, the higher the contribution. And in addition, if we look at row 4 versus row 1, we see another way in which this column contribution matches our intuition. When we look at row 4, we have an MSU which has just 2 values in it. This means that if an attacker can reveal user number 4's age and country, they can completely identify the rest of row 4's information. Compare that to row 1, where the attacker would need 4 pieces of information to have the same effect. This is weighted accordingly in the contribution. Finally, this score is normalized by the number of MSUs present, which means that when we have data sets with different number of attributes, we have an understanding of the underlying dynamics and what that means, even though a different number of attributes are present. This column contribution comes from the previous SUDA literature, as does the row score. This score is calculated as the factorial of the number of attributes minus the size of an MSU, summed over all of the MSUs in a specific row. This is supposed to be a score that weights the re-identification risk of every row, which corresponds to a user in our data set. And so once again, I'll show an example where we have in this row only 2 MSUs, one of size 3 and one of size 2. The MSU of size 3 contributes 2 factorial, while the MSU of size 2 contributes 3 factorial for a total of 8. Once again, the size of the MSU, the smaller it is penalized. However, there's no normalization term here, and this score is very dependent on the number of attributes present. In the context of Ads Data Hub, we'll have many different varying number of attributes, so it's very important to us that the score that we develop makes sense between data sets with different number of attributes. Because of that, we introduced the Probabilistic Identification Risk and Attacker Estimate Score, or PIRATE score. This score is the product of our work this summer, and we have presented the theoretical background as well as our algorithmic implementation to our sponsors at Google. The PIRATE score arises from the following problem. What is the number of times an attacker needs to pick attributes from our data set in order to have the necessary information to reveal that row's information? So if we have, if the attacker is picking attributes one at a time, in this case, we're going to assume that that's all attributes are equally likely. However, this can be modified depending on the context. We want to know the number of attributes that need to be revealed, which is exactly the expected value from probability theory. The definition of expected value is shown here. It's the probability of an outcome weighted by that outcome summed over all such possible outcomes. And now Miguel will discuss how we actually compute the PIRATE score.
Thank you, Aviva. So we're going to start with a little example here, and we're going to build out a probability tree. So there's lots of different ways that an attack scenario like this might play out. And to look at all those probabilities, we're going to build out this tree. So in this example here, we're going to have a data set that has 7 attributes, and it has 2 different MSUs for one particular row. So we're going to encode this information into a node here. So we're just going to say the number of attributes in this first MSU, the number of attributes in the second MSU, and now the number of attributes which are left over, which are not identifying for this particular row. So now an attacker is going to reveal an attribute randomly, and it might be from any of these 3 groups. It might be from either of the MSUs, or it might be unhelpful to the attacker, and it might be not from an MSU at all. So the probability of this happening randomly here is 3/7 from this first group here. So the probability that they're going to get an attribute from MSU A is 3/7. And we can build this out for MSU B and also for non-MSU attributes. So here we're getting the probabilities of all of these different scenarios happening. And we can build this out, and eventually we're going to run into a node like this. We call this a terminal node because all of the attributes from MSU B have been revealed. And that means that the attacker has won, and they have identified this row that they're trying to identify. So all of these are different situations that can happen. In this case, first they revealed an attribute from MSU B, and then in their second reveal, they did the same thing over again. And all of these nodes encode different possible situations. Now the probability of any one of these situations is just the product of all of these probabilities individually, going from our terminal node up until the root node. And now we're trying to find the expected value of the number of attributes which needs to be revealed. So in this case, the attacker revealed 2 attributes, and then that was enough to identify this row. But you can imagine that they might not get so lucky if first they reveal a non-MSU attribute. So eventually, as we build out this tree and you keep removing attributes, all of the leaves in this tree will be terminal nodes because you'll run out of attributes. So then this expected value is going to be, for every terminal node, the depth of that node multiplied by this product of all those probabilities up to the root node. If we remember the expected value, it was probability times outcome. Here, this product is our probability, and this is our outcome. And now, from that example before, that root node, that terminal node that you saw, had a depth of 2 and the probability of 2/7 and 1/6. So here, this was our contribution from that one terminal node. And once we take the sum over all of our terminal nodes, that is exactly our expected value that we're looking for. So this is how we're going to calculate our PIRATE score for every single row, which has MSUs. But one thing that's a little bit different is that MSUs can overlap. So there can be MSUs like this. So you see here 1 and 5 are attributes that are present in more than one MSU. So we have to keep account of those differently. And the way we do that here is that for every MSU, we keep a track of only the number of attributes which are uniquely only in that MSU. And then separately, we keep a list of what we call overlapping attributes. And these are just the attributes which are in more than one MSU. But once we do this, we can build out our probability tree in the same way because it's possible to draw a unique attribute from MSU A, B, or C, or an attribute which is not in any MSU, or any one of these overlapping attributes here. But our definition of a terminal node has to change a little bit, because a node is only terminal if this unique value here is 0, but also if the overlapping attributes from that MSU have also all been drawn. But once we account for that, we build out this same probability tree, and we calculate our pirate score in the same way. And we went ahead and we applied this to some simulated data that Google gave us. So they gave us 4 different tables to mess around with, and these are all sandbox data. So that means that the fields have the same titles that they would in the real Google data, but the values are not necessarily representative of what's in the actual customer's data. We decided to investigate this impressions data set because it had lots of fields that were identifying, such as a person's age or a person's location. So we went ahead and we did this, and we picked 30,000 rows from this table, and we ran several different experiments where we investigated different attributes. Now, these first ones that we picked were publisher domain, query language, mobile browser class, and campaign ID. These all have to do with how a person saw this ad, what browser were they using, what language was the ad served in, things like that. So first, we ran this through Suda, and we got back 16,000 rows that have MSUs. Now, out of those rows, we ran a pirate score on each of those, and they had an average pirate score of about 2.4. So that means, on average, if you wanted to attack a row in this data set, it would need to be one of these 16,000, which has MSUs at all. And then you would need to know about 2 or 3 attributes of a person until you could identify them. And we want to look at also which attributes are doing that identifying. And that comes back to this column contribution here. So here we can see that publisher domain and query language were the attributes that were the most identifying in this specific experiment. And query language is identifying because there are many different languages in this data set, and they're all uniformly likely. So any one particular language only had about a few hundred examples of people who spoke that language. So once you knew a person's language, it really narrowed down who you might be looking at. And for publisher domain, there were many unique domains where people saw these, so this was also a very identifying attribute. On to this second experiment, we decided to look at more classic demographic data. So gender, age group, country, all 3 of these have to do with location: country, region, and metro. But now when we ran this data set through Suda, we only got 124 rows out of 30,000 that were identifiable at all. So that lets us know that this combination of attributes is in general much less risky. And then for those 124 rows, the average pirate score was 4.4. So you can see there's only 5 attributes here in total. So on average, you needed 4 or 5 out of these to be able to identify a row. And you couldn't identify very many of them at all. Now here we can see that country is not identifying at all. That's because every single person in this data set was from the United States. So country was totally uniform, and it wasn't identifying. As for region, region was not uniform, but there were only a few possible values, and they were spread very evenly over these 30,000. So once you knew a person's region, there were still thousands and thousands of people who also shared that region. So that's why region is not identifying in this example. And as for our final experiment, here we stacked a lot of these same attributes from before and did a larger experiment. So now once you're allowed to use all of these attributes, the number of rows that have MSUs goes up to 25,000. And that makes sense, because the more attributes you have about any particular row, the more likely you are to be able to identify them. Out of these 25,000, our average pirate score was 4.4. And now if we look at these contributions, we can see that query language was very identifying before, and it still is. And country, since it's still uniform, is still not identifying at all. And then here we can see that region, which used to have a 0% contribution, now is able to contribute because you're able to combine it with some of these other attributes and still use it to identify certain rows. And now Sarika is going to come up for some concluding remarks.
Okay, thank you, Miguel. Okay, so in summary, our goal for this summer was to calculate the risk of privacy leaks occurring in Google's Ads Data Hub. We found that in the existing Suda algorithm, the column contribution score still provides useful information to us, but the row score does not. This is where we created our new measure called the pirate score. Okay, so to remind you, the pirate score is the probabilistic identification risk and attacker threat estimate. It's an identification risk, as said in the name, and we calculate it using the expected value. So what is the expected number of attributes that a hacker or attacker would have to know in order to uniquely identify a row? In order to do this, we use probability trees, as Miguel explained. So just some recommendations for future work. So our current pirate score assigns a score for each row in a data set. as I mentioned in the introduction, Google's Ads Data Hub employs an aggregation constraint. So what does our single row score translate to once the rows are aggregated? Another potential area for future research is mitigation techniques. So once we have the pirate score for a data set, how do we use that to reduce the risk of these leaks occurring? Lastly, in practice, we know that attributes are not all equally accessible in reality, and that some may always appear as continually risky. So for example, gender or age group are more likely to be known to somebody than what ad or what campaign ID a person saw. In the same way, some attributes such as, let's just take age for example, may always show up as being risky and present in different MSUs, so we'd want to reflect this in our pirate score. So updating based on the queries run or just what's seen before. Lastly, we'd just like to thank our industry sponsors for being with us today, especially Verdun Akopian and Scott Schneider, who hosted us twice this summer for 2 site visits, our academic mentor, RIPS director, RIPS program manager, and just the rest of IPAM, as well as you all for just being here with us today. We are so grateful to have had this opportunity, and we would not have been successful without you all. And now we will open up for questions.
Yeah.
So I'm not sure exactly how you're implementing it, but it seems as though constructing that tree would be fairly intensive, and also it seems like when you construct on those trees, it's only for one row of the table.
Right.
So was there any consideration of runtime, and how important is that for applying this?
Yeah.
Applying it as well?
Well, yeah, it's a good observation that building out this tree, the trees can get very large very quickly. But it's worth saying that we got a bunch of sample queries, so we could see how oh wait, I didn't repeat the question. The question was, don't these trees get very big? Isn't it very computationally expensive and hard to do? And in the queries that we saw, we looked at some customers' queries, and usually they only were looking for between like 4 or 5 or maybe tops like 10 or 15 attributes. So even though this doesn't scale very well with the number of attributes, the scale that we're working on is never really that big that it becomes a problem.
Could you go to the column contribution slide?
Yes, I can. Yes.
The example.
Oh, yep.
Can you just explain again where the 7 comes from? Because I was kind of confused about that.
Yeah. So the question is here on this column contribution, where is this 7 coming from? So Aviva.
Sure. So 7 is the number of MSUs present. So if we count for all 5 rows, the number of MSUs that we've found, there's 7.
There's
so we
8.
can or
There's actually 8.
oh no. Well, in that case, there's a mistake. So if there are 8 MSUs present,
Yeah. Great.